Hello everyone, welcome to problem 3.25 of David Griffiths Electrodynamics. So I'm doing this slightly differently than I've done previous videos. So I've recently bought an iPad, and so I'm going to try this out as an option for for recording my videos. Sorry, I'm a little sick today, under the weather, but we're gonna give this a shot and just see how you guys like it. I think it works better for me because I can do this. It's a little bit easier for me sitting down, being able to be at my desk and look at resources while I'm trying to solve the problem myself. And rather than being at the whiteboard, although the whiteboard is useful if I really just need to get some thoughts out, but I figured this would be nice because I can also keep my solutions in a nice little document and refer back to them if I need it at some point. So we're gonna go on and just we're gonna do this problem now. So looking at the problem statement, it says to find the potential outside of an infinitely long metal pipe of radius capital R that is placed at right angles to an otherwise uniform electric field E naught. And it also wants us to find the surface charge that is induced on the pipe. Okay, so first we need to find the potential V naught. So I've written it here. I don't know what the best way is to highlight things. I'm gonna go with if there's a way I can just underline maybe, or do it without actually. I don't think that's what I want. Well, we're just gonna go with a highlight for now, I think. So hopefully you can still read it as I highlight it. So we're gonna find the potential V naught outside of an infinite metal pipe, and I've drawn the diagram here on the left, and we have a cylinder that we're kind of looking at it head on, so we're looking into the cylinder, and so coming out in and out of the page is the z-axis, to the right is the x-axis, up and down is the y-axis. So that's how I defined it, and it has a radius of capital R, and then I've drawn some arrows to represent the uniform electric field that has a uniform magnitude of E naught, and it's in the x hat direction. So it's at right angles to the pipe. Now, the pipe, it says it's metal, so therefore it's going to be a conductor. We're going to assume a perfect conductor, and due to that, there will be a induced electric field due to charges being moved around and essentially polarizing the pipe. So positive charges will move towards the right side of the pipe, and negative charges will kind of come to the left side of the pipe here in this second diagram I've driven, which will then induce its own electric field going going this way, that kind of opposes the external electric field. So really there's two electric fields going on here, and so that will create the actual electric field outside of the pipe will, instead of being straight lines because of the an external one, that will kind of be curved. We don't know the exact shape. That's not what our goal is here, but you can kind of just picture that as a situation. And because the pipe is a conductor, we know that it is an equipotential due to it being a conductor, like I said here. And we know that if the potential then, it's an equipotential due to it being a conductor, which means the potential is constant throughout the volume of the pipe. And so we know that if the potential is constant, then the electric field inside the pipe is zero, and we know that the electric field inside conductors are zero. since the work done to move a charge inside of a conductor is, there's no work being done, so the electric field must be zero. Or you can get it from the fact that the electric field is just the gradient of the potential. If the potential is a constant, then you just take the derivative of a constant, which is zero. And so that means for r, which we're going to use r as the radial distance from the cylinder. So you can just think of r as some, distance away from the cylinder, and then phi is going to be well, I guess in terms of this, it'll be the traditional angular, angle phi here in terms of how we've drawn this diagram. So that means for r less than or equal to capital R, the radius of the pipe, the potential is zero, because it has to be zero. Well, we're going to define the potential to be zero. We need to define the potential to be zero somewhere, because the potential has to be in reference to something else, like some reference value. So we define it to be zero. It's constant throughout the pipe. And if we set the I said here that we define the YZ plane, so the plane that's going in and out of the page along the y-axis. We define that plane to be zero, kind of splitting the pipe in half. And it's also going to stay zero all the way out to the radius of the pipe, since the pipe is an equipotential. So that's one condition we have. And then we also know that at large distances of r, the induced electric field, the fringe field from the induced field, should fall off, as it's not going to be very strong. And so at large distances, we shouldn't even notice the effects of that induced electric field. And so we know then that at large distances, the electric field should just be the external field, which is just E naught x hat, which is given to us. So then we can find from that at large r, we can find the potential at large distances, just approximating and getting rid of the fringe field effect. So, the potential is just the negative integral of E dot dr. So E is just E naught or minus, yeah. The electric field here, you can see. There should be a minus sign here. Oops, sorry about that. Should be, sorry, I'm still in highlighter mode. Should be a minus sign here. The electric field is E naught. We pull it out of the integral, and we're just integrating dx x hat. And so we just get minus E naught x. Or writing it in terms of the cylindrical coordinates, x is just r cosine phi. So the potential is minus E naught r cosine phi at large distances for r. And so, and here I just said where r is the radial distance from the cylinder, and phi is the angular coordinate from the x-axis. And so using our result from problem 3.24, which the problem statement recommends, I've written out the full solution. So this solution is the, let me just kind of box it in here. This equation is, well, that's not great, but let me just kind of do it myself. This equation is the general solution to solving Laplace's equation in cylindrical coordinates, assuming that we have azimuthal symmetry, so there's no dependence on the z coordinate. So this is what we found in the previous problem. And so taking this, and then we basically figured out our boundary conditions. That is, the potential is 0 for r less than or equal to capital R. That's our first boundary condition. I'll highlight that. So this is our first boundary condition. That is not what I meant to click on. And then our second boundary condition is that the potential is negative E naught r cosine phi when we're at large distances for r much greater than the radius of the pipe. So if we just compare these boundary condition potential like what the potential reduces down to for these two conditions, and compare it to the full general solution, we can see that A naught, B naught, B sub k, and D sub k must be 0, like I've written here. Because, well, if you just look, like if you just plug in like capital R, or plug in large values of R, this whole general solution should reduce down to these things given those conditions. So, and we there's no like just constant term in our equation here, in our boundary conditions here. There's no natural log term, so we know A naught and B naught just must be 0. There's no sine terms in our boundary conditions, so we know that the coefficients on the sine term should also be 0. So that's how we're getting that. So then I just rewrote here the solution, getting rid of those terms, so it's kind of more simplified. So our potential then must be the summation from k equals 1 to infinity of r to the kth power times the a sub k coefficient cosine k phi plus r to the minus k power c sub k cosine k phi. All right, so that's what our general solution has reduced down to, just looking by observation. Now, if you also just observe, so we have this summation here from 1 to infinity. If k is like, let's say k is 2, 3, right? Then we're going to have r squared, r cubed, r to the 4th power terms. And then vice versa, we're going to have r to the 1 over r squared, 1 over r cubed terms. And obviously those kind of terms don't appear in our boundary conditions. We only have an r, like a linear dependence on r. So, excuse me 1 second. We only have a linear dependence on r, which means that our summation probably just reduces down to the k equal 1 term. So we can just kind of assume then that our summation is, we can get rid of the summation and just have a single term. So kind of with that approximation then, we basically have this. So just for the k equal 1 term, we have a sub 1 r to the 1st power times cosine phi plus c sub 1 divided by r, because it's r to the minus k power, so r to the minus 1 times cosine phi, or just rewriting it like this, factoring out cosine. Then this is now our potential reduced down even more, our general form, and we can apply our boundary conditions a bit more. We can actually like start to apply our boundary conditions directly here. So just from a pure observation, we can tell that taking the first boundary, or sorry, the second boundary condition, so that the potential must be this minus e naught r cosine phi when r is much greater. Then, so when little r is very big, the second term goes away. This term goes away because that will approach infinity, and so 1 over infinity is 0. However, so this term, we basically have a1 times r times cosine phi, which is basically exactly what this boundary condition is here. So we know that a1 then must be equal to minus e naught. And so I kind of box that in. So that's, we can deduce that coefficient from boundary condition 2. And then applying this first boundary condition, so the potential is 0 when r is equal to capital R. Just from physical intuition, like cosine of phi, we have this multiplication here. So cosine of phi, the only time that's going to be 0 is when phi is, cosine is 0 at, when at 90 degrees or whatever. But there's no reason that the potential should, kind of go through that kind of behavior. There's no like, if you look at our potential, yeah, I mean, there's no reason it should go away with the phi depends. So our intuition should tell us that it goes to 0 based on the term in parentheses. So we can set that to 0, and given that a1 is minus e naught, we can write that as like here, minus e naught capital R plus c1 over capital R equals 0, and then just solving for c1 here, just doing some simple algebra, you can get that c1 is equal to e naught capital R squared, and I boxed that one in just to keep track of it. So then, given those two coefficients, we have our potential. So just plugging everything in, you get that the potential at R and phi is minus e naught R cosine phi plus e naught R squared divided by little r cosine phi. And then just factoring out e naught cosine phi here, you can just rewrite it like this. And then factoring out little r, you can get this final expression here at the bottom. So you can get it in a nice cleaner state where it's, r over little r squared minus 1, and then factored out is e naught R cosine phi. And that is the final form of the potential for the, outside of this infinitely long cylinder. And now we need to move on to finding the surface charge density, which I did not do ahead of time. So we're going to do that right now. And in Griffiths, you can find, I forget what page it's on. I want to say it's somewhere in chapter, might even be chapter 2. I forget, but there's an equation in Griffiths. So the surface charge can be calculated as minus epsilon naught times the normal derivative of the potential. And I believe this comes from some kind of boundary condition. So this will be the normal direction is going to be the radial direction, and so this needs to be evaluated though at r equal to capital R, which is the surface. So this should give us, evaluating this should give us the surface charge density. So let's just go ahead and plug this stuff in. So we have minus epsilon naught, and then the potential, right, is this, and so we're taking the derivative with respect to r, which means that the cosine term is going to be constant with respect to this derivative. So we should have, we have that, and then let's see. So that r there at the bottom is going to be a part of the derivative. I guess I can just bring that out, and then we have the derivative with respect to r of r times r squared over r squared minus 1, I believe. I mean, would this just be easier to I think this would be easier to just, instead of trying to do like the product rule here, let's just like multiply this through. So we'll do the derivative with respect to r of r squared over r minus r. So we can take the derivative of each term independently. So let's do the derivative of the first term. So the derivative of r squared over r, well, that's going to be the derivative of this, which is constant r to the minus 1. And if I remember, it's been so long since I've done math, to be honest, but I'm pretty sure you bring down the power. Yeah, because the derivative of r, like x squared, is 2x. All right, so you bring down the power, decrease it by 1, which would bring it to 0, right? No, sorry, you decrease by 1. It'd be -2. So, oops, that's not what I meant to do. So, we have negative r squared over r squared. And then the derivative, obviously the derivative with r of minus r is going to be -1. Okay, so we know those two derivatives, and we can plug it back in. So sigma is going to be minus epsilon e naught cosine phi, just keeping these constants out. Really, I could bring r squared out too. And then we have, so the derivatives were -1 over r squared -1, right? So that's what that whole term would have evaluated to. I'm just trying to see if there's any other simplifications I need to do here. Okay, so let's do it this way. Let's write it as, so this equals minus epsilon naught e naught. Let's move the r squared back in, and then let's put the cosine out front. We can factor out the minus signs from here, and then that will cancel the minus sign out there. So this will just be a plus. And then we get r squared over r squared. It's minus r squared, and then cosine phi. But remember, we got to evaluate this at r equal to capital R, right? Because we want the surface charge density at the surface. We want the charge density at the surface. So then we know, so the surface charge, the surface charge density then is going to be, so surface charge density at r is going to be epsilon naught e naught. This first term cancels out. You just get minus r squared, so there's going to be a minus sign, minus r squared cosine phi. I think. Is that right? Or did I? Oh, you know what? I think this r squared factor here. Oh. Yeah, I pulled out this r squared, and it's only in the first term, and I didn't like divide by r squared. So really this should have been, really, when I factored that out, this would have been like 1 over r squared, which means when I multiplied it back through, this would have been a -1, right? So that would have been, that would have been 1 minus 1? I'm just trying to make sense of this. Hang on. No, because I factored out the minus sign. I'm an idiot. Sorry, guys. I factored out those two minus signs. This would have been a +1. So this would have given us then, let me erase this answer. So we don't have a negative, we just have a 2, because this, at r equals r, this becomes 1 plus 1, so that's a 2. We have 2 epsilon naught e naught, and then cosine of phi. That looks correct. I don't think I see any issue there, did I? All right, I think that is the final answer. If you guys catch anything that I did wrong, please let me know. I did this part kind of live, so yeah, there was some like actual thought process, I had to slow down and kind of think about this myself. So anyways, that is problem 3.25. So yeah, if you guys have any questions, let me know. And yeah, give me suggestions, give me tips on things that you like. And if you like this format better, I certainly like this a lot better myself. It's much easier to do. You know, I'm probably going to stick with it regardless, but I think this will be nice because it gives you guys a full screen view of the math. And, you know, the whiteboard was nice, but I think this is going to be better for the long-term sustainability of making these videos. So thank you guys for watching, and hope you guys have a great day.